Welcome to Make, a course taught at the University of South Florida. This tutorial is about controlling the I2C LCD display with the Arduino. We will discuss serial communication with the I2C bus, LCD displays, and the use of a third-party C++ library to control the display. Let's discuss the LCD display hardware first. Here you see the backside of the LCD display that's supplied with the Arduino kit. And basically what they did is they used a standard HD4478 standard LCD display, and they piggybacked onto it a module that does the I2C bus communication, and it also controls the brightness of the LED backlight. So a typical standard LCD that obeys this standard, that has a fairly large number of input pins. It uses a parallel interface, and so what we have here down here, there is a schematic of that display, and of course we have a power in and ground. Then there's a pin that allows to control the contrast. We have a pin that allows to select a register into which the data is being written, then or read from. Then we have a read or write select pin. Then we have an enable pin. So this enable pin, basically when it is high, then only then data can be written into the display processor. So the remaining lines here are the data lines. One can either use all 8 or only 4. This depends on some settings inside the display. This particular display setup uses only 4 data lines. And then the remaining pins are to turn off and on the backlight. And we have another ground connection here on pin 16. So if you only had the display and you wanted to directly control it with the Arduino, you would have to control all these lines with the Arduino. So you would have to use at least 1, 2, 3, 7 pins of the Arduino, and that would of course limit your options to connect other things to the Arduino. So the great thing about this display is that it has this I2C module attached to it. And the I2C module, that essentially connects all these pins of the display to just 2 pins, the SDA and the SCL pin on the module, with which you can control the LCD from the Arduino. So let's examine how the I2C module is connected to the display. This is shown here. The red arrows, they try to show what's hooked up where. So first, the blue block, that is the potentiometer with which we can adjust the contrast. So if your LCD display doesn't look happy, then just put a screwdriver in there and turn the potentiometer left and right until you experience good contrast. The most important part on the module is the PCF8574 port expander, and this chip essentially is controlled through the I2C bus, so it's directly connected to SDA and SCL here. And then it has all these pins that essentially function like Arduino digital pins. So with this module, you can not only drive such an LCD display, but you can use it for all kinds of purposes where you don't have enough digital pins on the Arduino. So here we use these 8 pins that this module has to control the data lines, and of course the read, write, enable, and the register select lines. The final part here is this jumper that you see. on the module. This jumper actually allows to directly turn the backlight off or on. So if you have an application where you don't use the backlight, or you want to control it through some other mechanism that, for example, the Arduino could turn it on or off, you could take the jumper off and then connect the relevant pin to a power source that you can control. So for our application, we leave the jumper on. That simply means that the backlight is on by default. So there are a few more pins on this chip that are not being used to control the LCD display. These are the address pins. So these are these pins actually. And with these pins, the address of the port extender can be modified. So the port extender has a I2C bus address that is preset in the factory, which is 0100. And then we have 3 pins that we can set high or low, set to 1 or 0, and with which we can then create the full 7-bit address of this chip. Now in this particular case, all 3 pins appear to be connected to 5 volts, so the LCD display has the address 01001111 because these 3 pins are on 5 volts. Unfortunately, there is no way to change this without doing some soldering. It's difficult to connect more than one display to the Arduino at this point. One more little detail. You may have noticed that I wrote here 0B before the binary number, the address number. That is a C++ convention to identify binary numbers. One could also express this number as a hexadecimal number. Then we would write here 0x to tell the reader that the following digits are hexadecimal numbers. After I made the tutorial, I realized that I made a mistake when describing the hardware of the display. As you will see in the tutorial, the Arduino is able to control the backlight of the display directly. So that means that the backlight is actually the backlight pin of the LCD is directly connected via a resistor to a pin of the port expander, and by setting the pin high or low, one can turn on or off the backlight. Now let's discuss the I2C hardware. Here you see a schematic how the devices are connected. Typically we have one or more master devices. In our case that would be the Arduino. And that Arduino is connected through 2 wires, the clock wire and the data wire, SCL and SDA, to all the other devices. So here this would be the slave devices. They would simply also connect to that 2-wire bus. There are usually 2 pull-up resistors, one for each of the lines, and these resistors make sure that the lines are at 5 volts if these devices that are connected do not pull them down to 0. So I2C devices typically have not the capability to apply 5 volts to the bus, but they are able to pull it down to 0. So they are essentially only able to sink current, but not to supply it. So that is the reason why the I2C bus, which stands for Inter-IC, is also sometimes called 2-wire bus or also IIC bus, because of this 2-wire feature. So because we only have 2 wires, of course there needs to be a method that we can address individual devices that are connected to this serial bus. And that is done via addresses. And in the I2C protocol, all devices have a 7-bit address. So that would enable, in theory, to connect 128 devices to the bus. However, a few of these addresses are reserved for a special for special kinds of commands. A particular example is, for example, a command that would broadcast to all devices, right? So you could tell all devices something at the same time, and they would all listen. 7 bits, right? There is one more bit to make a byte, and that's 8th byte. That 8th bit is used to tell the device whether it is expecting a read or a write operation. So whether we will read something from a register that is inside the device, or whether we will write something into a register that is in the I2C device. This slide shows a typical scenario how the I2C bus might be used in a circuit. Several devices are being connected to the microcontroller. In this example, actually there are 2 microcontrollers, so we basically have 2 master devices, and then we have a bunch of slaves here. These devices can be LCDs, memory, something like variable gain op amps, oscillators. All these types of chips or devices are being available in I2C versions, and so that makes it very convenient to connect everything together and control it with a microcontroller, the Arduino. So the addresses of these devices, they are basically these 7 bits that I just talked about, and usually the manufacturers, they fix a few of these bits, and then they allow the user to select the remaining bits through setting pins low or high that are on the chip package. On this figure you see a schematic of a typical communication sequence between the master and a slave. So first we have a start signal, then the master sends the 7-bit device address, followed by the read or write byte. Then there's actually an acknowledge bit that is being sent from the slave, right? That it received the address, and then the master sends some information what to do with the data that is being sent after that. And so here they call it the 8-bit register pointer, but often this is also called a command or control byte. So here we basically tell the slave device which of the registers will be affected, and then once this has been sent and the slave acknowledges again, then the data bytes are being sent. And in between the data bytes there's always an acknowledge signal, so that the master knows that the slave was listening. Once the transmission is over, then very important, the master sends a stop bit that tells the slave that the communication is over. So in the example of the LCD display that we're discussing in this tutorial, this here would basically be the address of the port extender. Then there would be a 0 for write, and then here we would basically tell the LCD display into which register we are writing something. So we could here tell it, for example, okay, this is the register that contains the text that is visible on the display, and then each of these bytes here could contain a character that is supposed to be displayed on the display. Now we have a basic understanding how I2C data transfer happens. I downloaded the data sheet for the PCF8574 port expander. We see already it's an input-output expander. So in effect, this chip can not only be used to output digital signals, but we can also actually read digital signals and then transfer that data back to the Arduino. So it supports both read and write I2C operations. So I scrolled forward to the block diagram of the device that's in the data sheet. That's what we see here. And you see here all the pins that are on the chip. We have the 2 I2C lines, the data line and the clock line. We have the address lines. There is a power input. This here is the 5 volts, and this here is the ground. And then we have the 8 digital pins. And there's one additional line. It's an interrupt line. So depending on conditions on the inputs, this chip can actually launch an interrupt that can talk back to the Arduino and tells it that it is time to inquire what happened at the input-output port. So when an address is put on the bus, then depending on these address lines, the I2C bus control circuitry that's inside this chip decides whether it needs to listen further or can ignore what's coming. So if the right address comes, then this bus control starts listening for the following data bytes, and these data bytes are then evaluated and written into the register of this chip. This chip has only one register, so we can simply put a byte of ones and zeros into this register, and then these ones and zeros are transmitted to the port controller that then sets these pins here to high or low voltage, 5 or 0 volts. When it's used as an input, this chip, then some voltages are being put on these pins from some external sources, and then the shift register is actually set depending on the voltages on these pins, and then the I2C bus control can actually output this data onto the bus when the master device is asking for it. Now I scrolled forward to the pinning chapter. Here you have a list of pins of the port expander chip. This is the standard package with 16 pins. So here you see the 3 address lines, then those denominated with P, 0, 1, 2, 3, 4, 5, 6, 7. These are the digital pins. Here this is the ground connection, this is the 5 volts, and here we have the I2C pin, and that's that interrupt pin. This pin comes in several different packages. 16 pins we just saw. Here there is one with 20 pins that has a few non-connected ones. So it's always important to understand what package one works with and which pin is which. Okay, so let's move on to the communication protocol. So here we have 2 graphs. This one here is for write and the next one is for reading. And so what you see here now is a detailed description of the bytes that we can send to the chip. We know that it has only one register, so this is a very simple protocol. Essentially all we do is we send a start condition, the master sends a start condition, then we send the 7 address bits, and then the read-write bit, and then here in the case of writing, we then send a data byte. And you see here that one could also send a second one and a third one and so forth until a stop condition is being sent. So this would enable actually to use this port extender to transmit varying data over time. So you could use it as a parallel port, for example, and simply turn it on once and then send data bytes that would be subsequently put on the digital pins of that chip. So when we use it as a when we read it, then a similar thing, we again send the address and the start condition, but here now we have a 1 for reading. After the master sends the address byte with the read condition, with the read bit, then the slave starts sending out the bits that correspond to the conditions of the 8 digital pins. And this process continues until the master sends out a stop condition. So with this one can continuously monitor the state of the pins as input of that port extender chip. Let's see the I2C bus in action. I connected the LCD display to the Arduino, and this video now shows us what the Arduino is doing before we will discuss the Arduino Sketch. So first we wrote make course, then we go left right, and then we add awesome on the second line. So here you see the 4 jumper wires that go to the Arduino, and over here we have the power connections, 5 volts and ground, and then these 2 jumpers, they go to the I2C bus connectors. Here's a better view of the I2C connections. When you turn the board around, you can actually see the markings for the I2C pins. So here we have SDA, that is the data line, and SCL, that is the clock line. Let's look at the Arduino Sketch that controls the LCD. We start out with include statements. The first include is the wire library. This is a library that is included with the Arduino IDE, and it essentially gives us all the methods that we need to operate the I2C bus. The second include statement includes the liquid crystal I2C library. This library was supplied by the store where we bought the LED displays. So this library contains all the methods that we need to operate the LCD display. Then we go on to the instantiation. So we say a liquid crystal I2C, and then we instantiate a display named my display. And the parameters that we have here in the constructor, that is first the bus address of the display. So that is essentially the address of the PCF8574 port extender. It's actually noted here in hexadecimal numbers. You can translate that into a binary number here. So you see the manufacturer preset part of the address, and then the 3 pins that are on high potential that give the lower part of the address. The next 2 parameters, they basically tell the library methods that we have a display with 16 characters per line, and we have 2 lines on the display. Okay, so we go on to the setup function. First, we use the init method that is supplied in the library. So we say here my display, the display name, dot, and then the method name, and we don't have any parameters in this method. So what happens here is the LCD is initialized. Essentially, there are things that need to be told to that library. For example, how many pixels are in each character. So this display uses a 5x8 matrix. And there are some other hardware related things that are being initiated. Worthwhile noting is that this init method also starts the I2C bus, so we don't have to put in the wire begin statement here in the setup. Then the next method that we're calling from that library is to turn on the backlight. So after this here, basically the LED, the white LED that lights it up, comes on. And then we do here the first print command. So we say mydisplay.print, and I put in here make course. And so this is in the video when you actually saw that make course appeared. Now here in the main loop, I simply took a few methods from the library and basically made some examples here. So the first part, this for loop, it goes from 1 to 9. that uses the method scroll display to the right. So essentially both display lines are moving over to the right by 10 characters, and between each of the shifts to the right we have a 200 millisecond delay, so we can actually enjoy what's happening. The next one, the next for loop, uses the scroll display left. So this is the moment when you saw the make course text move back to its original position. Again, we go here in 10 steps, so we go to the right and then we go to the left. And then I moved the cursor into the second line of the display, right? The display counts starting from 0, so 0 is the first line, 1 is the second line. Same with characters. When we say 8 here, it's actually the 9th character of that line. So we set the cursor into the second line to the 9th character position, and then we print here awesome. Well, and then we repeat it over and over again, so you see the texts scroll right and left and so on. So there are many more methods in this LCD display library. So it's a good idea to check out the header file. I opened it here in Xcode on my Mac. You can look at this in any text editor or also in the Arduino IDE. So here we have the CPP file, right? That has all the hard C++ code in it. And then here we have the H file, that is the header file. And so they start out here with a whole bunch of defines that essentially that goes into the nitty-gritty of operating the display. So all the commands that the LCD display knows are translated here from hex numbers into something that humans can understand. There's some flags and other stuff. Luckily, we don't have to really concern ourselves with this, because somebody else already did all the work, and we have this great library. That makes things so effective by using object-oriented programming and libraries, and also the I2C bus, right? Everything is plug and play. So this here is now a list of all the methods that we have here. Remember, classes. So we have the public class members, and these here are the methods. Further down here we have the private members, and these are many variables here, and also some low-level methods that are only being used inside the library. There's here something that sounds a little bit strange, compatibility API. API stands for Application Program Interface. Apparently, there was an earlier library, it seems, that used different names for the methods, and so they included some translation methods that actually translate these names into the new names that are up here. So we only have to look at this here if we want to know what the display can do. And while there are no comments, the names are pretty self-explanatory. So you can turn on a cursor, you can turn off a cursor, you can blink the cursor, you can delete everything that's on the display. There are a whole bunch of other things. The only way to figure out what they do is to play with it and use these methods when you operate the display. So one last thing, you need to remember when you run this Arduino Sketch that you put the Liquid Crystal I2C library into your library folder where all the libraries are on your Arduino setup. So here on my setup, I have it here in a library folder that is within the Sketches folder on the Mac. And so when you click here on the Liquid Crystal I2C library folder, then you see here inside we have the CPP and the H file. Okay, time for the in-class project. This time we will combine the proximity sensor with the LCD display. This project requires that you completed the previous in-class project and that you have a library for the proximity sensor. So the tasks are: connect both the LCD display and the sensor to the Arduino, and then modify the posted LCD demo code that I just discussed, and add the code for the sensor and show the measured distance on the LCD display. If there's still time, then please play with the various LCD methods that are supplied in the library. This concludes the tutorial about the I2C bus and how to control an I2C enabled LCD display with the Arduino. Thanks for watching.